Okay, so in this video, I'm going to go over the worksheet I handed out this week to many of the people I see in General Chemistry 1 for tutoring. And this worksheet focused on Chapter 2, which you guys just finished in class. So Chapter 2 starts with atomic theory, moves on to isotopic designation, and then focuses on primarily at the end chemical nomenclature, separating ionic bonds, covalent bonds, naming them, and also understanding some of the basic properties of that, and acid nomenclature as well. So in this video, I'm going to primarily just go through the answers to the worksheet. I might point out some things that are important conceptually here and there, but if you're having trouble, understanding where I'm getting some of these answers from the worksheet, I will have two videos that are coming very soon. One on acid nomenclature, that's a whole video on how to name acids, and then another video that's just on some, nomenclature guidelines. So if it's not up yet when this video is up, when you're watching it, it will be up very soon. So let's get started. So I'm going to just write the compound name next to each compound here, and I'm going to also specify whether it's an ionic or a covalent bond. Another word for covalent bond is molecular bond. So those two are interchangeable, covalent and molecular, but I tend to say covalent. So looking at 1A, this is an ionic bond. Okay, it's between a metal and a nonmetal. Beryllium's a metal, oxygen's obviously a nonmetal. Now, how we name ionic bonds is we keep the first element in its full name. So this is going to be beryllium. And then we take the second element and we chop off the ending and add IDE. So this is beryllium oxide. Spelling does count on these, and there's no partial credit generally. So if you're, don't know how to spell it, an element name, just look on your periodic table. I'm not great with spelling either. That's why I'm a chemistry major, not an English major. But so I make mistakes too. But they won't give you partial credit on these. So you want to make sure that you're spelling them correctly. Okay. So letter B here is also an ionic compound. Okay. It's between a cation of polyatomic ion, cation meaning positively charged. So this first polyatomic ion in letter B is called ammonium. Okay, and like I said, you really just need to memorize those polyatomic ions off of your formula sheet. And the second one here is called dichromate. So it's ammonium dichromate. So when it's involving two polyatomic ions or just one, that ending name does not apply as it did in example A, because those polyatomic ions come as full inclusive package, right? So they come with a charge and a specific name. All right, next guy is also an ionic bond. This is calcium, and that HCO3 is called bicarbonate. Okay, sodium bicarbonate is actually baking soda, and you bake with that. So this is calcium bicarbonate. You definitely don't want to go near that, eating it. Second one is an acid, so I'm going to call it an acid. I know it's an acid because it has a hydrogen ion right in front, right here. So this hydrogen ion kind of indicates to me that this is an acid, and then we will go through the naming process based on how many oxygen are at the end here in this case. So if you remember from lecture, you can name acids when there's an oxy anion in them, which in this case is that oxygen, based on how many oxygen there are, and the naming changes a little bit. So typically when there's one or two oxygen, for one you would put a hypo in the beginning if it's an acid, and you would also end chop off the ending in at OUS. So for example, HFO would be hypofluorous acid. Okay. Now, when there's two oxygen, you'll chop off the ending and you'll just make it chlorous acid. Okay, I'm sorry, fluorous acid in this case because it's chlorine. So this guy is fluorous acid. Now, I feel like I spelled that wrong because that doesn't look right. Yep, I did. So it's O before U before O. I make that mistake a lot. Okay, so fluorous acid like that. So when there's three oxygen, say this was HFO3, you add a ic ending. So this would be fluoric acid if it was HFO3. And when it's for oxygen, you keep the ic, but you add a per in the beginning. So this would be perfluoric acid if it was HFO4. Like I said, I'll have a separate video on that if that's not still making sense. Okay. Letter E here is a covalent bond. It's between two nonmetals, so we name that with prefixes. So this would be boron trifluoride. Why don't I put monoboron in the front? Well, when it's the first atom and there's only one, we don't put mono. So you'll never see mono in the first atom. If you do put mono, it's technically wrong. It goes against the rules of nomenclature. Okay? But if there's more than one on the first atom, we put the prefix. But if there's one on the second atom, we do include the mono. Okay? Letter F is an ionic bond. Now, keep in mind that this Pb is one of those transition metals, meaning it's indecisive. It can be many different charges. So you need to specify what charge it is in the compound that you're given. Now, in this case, I know that it's going to be lead 4 oxide. Now, how do I know it's 4? Well, I'll just kind of draw an arrow here to explain this for a second. So I know that oxygen's a fixed charged atom, meaning that it doesn't, change charge ever. So it's always going to be the same, unlike the lead, which can be a couple different things. So I know that an oxygen atom has a -2 charge. And I can see in this case that I'm given 2 oxygen atoms for every 1 lead atom, which tells me that the total charge of oxygen in that molecule is -4. Now remember that the net charge has to always equal 0 in a molecule. So if the oxygen is contributing a -4 charge, that means that the lead must be contributing a +4 charge because it doesn't have any subscripts, meaning there's only one atom of it. So in order to balance that out, it would have to be lead 4 oxide. Okay. So as far as being able to recognize that you're given a transition metal in the problem and, avoid not putting the Roman numerals, because if you don't put the Roman numerals, it's wrong. I would suggest if you're questioning whether it's a transition metal or not, you would just look at the periodic table and just verify that whether it is or it isn't. Because putting the Roman numerals when it's not is wrong, and forgetting to put it when you need it is wrong. So just be careful with that. All right, G is an acid, okay, same reasoning as above. And I'm not going to explain the nomenclature on this guy, but there's 4 oxygen, so you put the prefix per, and it's also ic. It ends in ic when there's 3 or 4, so it's perbromic acid. All right. Letter H is an ionic compound. It's between a metal and a nonmetal. So this is strontium, and that PO4 is called phosphate. It's a polyatomic ion. Okay. Letter I is an ionic compound. Now be careful. Copper is, that Cu is a problem child. It doesn't like to decide, so you have to specify what charge. In this case, it's paired with nitrite, which is a polyatomic ion, which has a -1 charge. So if I have 2 of those nitrite ions right there, that tells me that for every 1 copper atom, I get 2 nitrite atoms, each with a -1 charge, meaning nitrite contributes -2 to the whole compound, which means that the copper is going to have to contribute +2. Okay, so this would be named copper 2 nitrite. All right. Letter J is also an ionic compound. Gold, which is Au, is an indecisive problem child as well. So you need to put the Roman numeral. So in this case, it's paired with the cyanide polyatomic ion. So just if you don't recall that, that's cyanide. And it has a -1 charge. So I have 3 of those, which means that gold's going to have to contribute a +3 charge. So that's gold 3 cyanide. I spelled that wrong. So that's gold 3 cyanide. Okay. Chugging along here. Letter K is a covalent compound. It's between it's between 2 nonmetals. So it makes it covalent. So I'm going to have to use prefixes. So this is tetranitrogen. nona hydride. Okay, so how did I get that? Well, you add prefixes to both atoms in a covalent compound, but the first atom, similarly with ionic, you keep in its full name. So I kept the nitrogen in its full name, just added the prefix tetra for 4. Now, as far as the hydrogen goes, remember you chop off the ending and add IDE. So there's 9 hydrogen, which is nona. So it's nona hydride because I chopped off the ending and added IDE. Okay. Letter L is technically an ionic compound. It's more specifically a hydrate. Hydrate is a salt, so all of these ionic compounds between a metal and a nonmetal are salts. So it's a salt paired with water. So if you were to feel it in your hands, which you'll do a lab with, has a kind of a wet feeling to it, but it's a solid. So it's a little interesting. So all you do is you name the compound on the left, and then you specify how many water you have by saying the prefix of the number and ending it in hydrate. So example here, this is iron 2 nitrate. So this is the nitrate polyatomic ion. It has a -1 charge. There's 2 of them, and iron is one of the problem childs, and you need to specify its charge. So it's going to be iron 2 nitrate, and now I need to specify how many water I get. So I have 9 water, so I say nona again, and you end it with hydrate. Okay? So it's iron 2 nitrate, nona hydrate. So you do want to have like kind of a space in between those. It's not one word. So like I said, you name the compound on the you name the compound over here, just regular nomenclature, and you specify how many water there is by putting a prefix, and then hydrate at the end. Okay, so that's number 1. Number 2, typically going from formula to name is easier than going from name to formula. So this is kind of a little bit harder for some people, but if you're able to do, the others, it shouldn't be too bad. So first one tells manganese 2 phosphide. So these I'm just going to run through pretty quickly. So manganese, it's telling me is +2. Phosphorus, I know from the periodic table, is -3. It's in the group with nitrogen, so it has -3 charge. So what do? Well, I'm going to need 3 manganese for every 2 phosphorus. Okay, so I kind of swap the charges. So if you could do it like this, if you please, where you put manganese +2, phosphorus is -3, and then you kind of show that you're swapping it down there to put the subscripts. The only problem that this has is when you're going from this to this, you have to remember that whatever the number of atoms of a metal there is, in this case manganese, becomes a minus charge because the second atom in an ionic compound is always negative, the metal being positive. So just be careful with that. But if you want to do that, that's fine too. And this is an ionic compound. Okay. Next is sodium carbonate. So that's Na2CO3. So carbonate's a polyatomic ion, has a -2 charge. So sodium is +1. I need 2 sodium. Carbon disulfide, and that's ionic by the way. Carbon disulfide's covalent. So I'm just going to put carbon disulfide. Tells me there's 2 sulfur, CS2 like that. Okay. Lead 4 sulfate. So sulfate is -2. So if it's telling me the total charge on lead is 4, I'm going to need 2 sulfate atoms to balance that out. Okay. Iodic acid, so if you remember, the endings go as hypo for 1 with an ending of -ose, and the second for 2 oxygen is just an ending of -ose. 3 oxygen becomes an ending of -ic, and 4 becomes a per in the front and ends with an -ic. So in this case, iodic acid tells me that there's 3 oxygen. Okay, that's how I remember that. So this is, sorry, D's ionic, this guy's an acid. And if you're still having trouble understanding why that is, I'll have a separate video on that. So potassium permanganate, so potassium's a +1 charge. Permanganate's MnO4, it's a polyatomic ion. It has a -1 charge, so they balance each other out. That's ionic. Octaphosphorus trichloride, it sounds terrible, but really it's not. You just write phosphorus. Octa means there's 8, and chlorine tells me tri, there's 3. Okay, and that's covalent. Hypobromous acid, so remember, whenever you see hypo, it means just one oxygen. So this would be HBRO, okay, and that's an acid. Here we have another one of those hydrates for I. Now it tells me copper 2 sulfate pentahydrate. So copper 2 sulfate is going to be CuSO4 because sulfate's -2, copper's +2, so it balances it out. And I kind of put a star here or a dot, whatever you want, and I specify how many water I have. So penta's 5, so 5H2O. So that's copper 2 sulfate pentahydrate. Sulfuric acid's an acid. Sulfuric acid's one of those acids that doesn't really follow one of our nice rules for a couple different reasons, so you kind of just have to remember it. It's H2SO4. Okay. Hexaboron mononitride is obviously a covalent bond, so hexa means 6, so that's B6, and mononitride means 1 nitrogen. All right, last one here, we're almost there, is barium hydroxide. So barium hydroxide is BaOH2. Barium's a +2 metal. Hydroxide OH is a -1 charged polyatomic ion. Okay, so as you can see, the biggest key here is knowing the polyatomic ions. But if you don't know that, it's nearly impossible to do all this. Okay, so you really got to know the polyatomic ions. Moving on, number 3 deals with isotopic designation. So naming isotopes and getting some information from there. So in the question it says, zoom out a little bit, how many protons, neutrons, and electrons are in, and this did not transfer over properly, but I believe it said AS -3, 75, 33, like that. So sorry about that. And it wants us to identify the mass number and atomic number as well as the protons, neutrons, and electrons. So just as a review, if I have some arbitrary isotope, we'll call it A, and say I put a Z up here and I don't know, an X down here, Z is going to equal my mass number, and the mass number is the protons plus the neutrons, okay? And this X down here, that's a Z, this X down here is my atomic number, and that's equal to my number of protons, and it's also equal to my number of electrons in an atom. So that's how I would find the electrons. So the reason why the mass number is just protons and neutrons is electrons have a very small weight. Protons and neutrons weigh a lot more, so they're negligible electrons when finding the weight of an atom. So we just consider the protons and the neutrons to be contributing to the weight. Okay, so that's the general structure of it. So I will rewrite the one that we're given down below here. So we're given arsenic -3, 75, 33. So as we talked about just now, the mass number in this case would be equal to 75, and the atomic number would be equal to 33. Now we also need to find our number of protons, neutrons, and electrons. So the number of protons is going to equal the atomic number, and that's 33. Now notice one thing is this -3 charge is very important. That tells me it's not a neutral isotope. It's not in its neutral state. It has a -3 charge. So a minus charge indicates I have too many electrons. So they're not balanced, the protons and the electrons. There's too many electrons if it's negatively charged. So in this case, the number of protons and electrons are not equal because it has a -3 charge. So because it has a -3, it means it has 3 more electrons than it does protons. So in this case, there's 36 electrons. I just added 3 to 33. Now for the neutrons, you're going to take the mass number, which is 75, and subtract the number of neutrons because, the number of protons. Because the mass number is equal to the protons plus the neutrons, if I know the weight of just the protons, I can then subtract from the mass number the number of protons, and that would give me just the number of neutrons alone. So this obviously kind of works both ways. If for some reason you're not given the number of protons, you can get the number of neutrons. If you're for some reason not given the number of protons, you can get that number from taking the mass number minus the number of neutrons. So it works both ways. But in this case, the neutrons are going to turn out to be 44, I think. I'm not good at mental math. So there's 44 protons, 44 neutrons, and 36 electrons. E minus is electrons. Okay, so be comfortable with that isotopic designation. Number 4, you're not going to be asked a lot about this in general, but I can guarantee you on your first exam, you'll have some question about atomic theory. It becomes bigger in the later semester towards like Thanksgiving time, but you should know, what Rutherford, Millikan, Chadwick, who else is there? You have Bohr. Am I remembering everybody? I don't want to leave anybody out. Well, let's see. So Rutherford discovered the nucleus. He described it as a densely, that's not spelled right, densely, but I don't feel like fixing it, a densely packed area of positive charge. Because remember, when you look at an atom, you have the electrons that kind of sit on the outskirts. So all those green dots are electrons. And then in the center of the atom, you have the nucleus. And the nucleus has protons and neutrons. But remember, neutrons don't have a charge. So when he did this experiment, he said, oh, the center of the atom is positively charged, and I'm going to call it a nucleus. He didn't realize that there's neutrons in there because the neutrons don't have a charge. He did this via what we call a gold foil experiment. Okay. Millikan discovered the charge on an electron. We also call this the the oil drop experiment. So long story short, he basically used a oil dropping mechanic to drop positively charged particles into an oil, and then realized that they're not always coming out still positively charged. They're coming out with some kind of different net charge, which told him that something funky is going on. There must be something negative in there, and that's how he got to the negative charge of the electron. Chadwick is not super important. Well, they're all important in my heart, but he's not the most important out of all of them. Chadwick discovered the neutron. That looks terrible. Now, Bohr is going to be very important starting, like I said, end of the semester around Thanksgiving time. Bohr really was debunked the typical understanding of the conceptual idea of an atom. He took this idea of what Rutherford said with, has a dense center and exact rings on the outside, and he kind of, flipped it upside down. So in short, he really contributed to the fact that electrons don't just float in the atom randomly. Electrons move in what we call a fixed orbit, meaning there's an actual rhyme or reason to the way they move. They don't just move all, lackadaisy. So that's 4. Rutherford actually also discovered protons in his kind of quest of discovering the nucleus. The only thing you have to be careful with is that Rutherford so the first thing he did was discover the nucleus. And then about 10 years later, he also discovered protons. So that's just one thing to keep in mind. Like I said, this is not super important, but you should know what each of these people did. It's not interesting either, but it is what it is. So we have Chadwick. I feel like I'm missing some people. Okay, yeah, I know who I'm missing. I'm missing my plum pudding guy, J.J. Thomson. So J.J. Thomson discovered the electron. Now, what is the difference between what Millikan did up there and what J.J. Thomson did? Okay, I'll tell you. So that's an M, by the way, right here. I'm writing in the wrong color. So J.J. Thomson discovered the electron. He said, okay, there's this thing called the electron. I don't really know what it is or what it does or the purpose of it, but I know it exists. Millikan came on later and said, okay, what's an electron? It has a minus charge. So, sometimes people will get that confused. So J.J. Thomson discovered the electron while Millikan discovered the charge on the electron. Okay, so that's a little bit. Oh, I did forget one person we probably should know about, Schrodinger, who I think is interesting. But once again, that becomes more handy later in the semester. Schrodinger is kind of known for the birth of quantum mechanics. So kind of discovered quantum mechanics and developed it. So sometimes it's called developed. Oh my God, developed. All right. So not super interesting, but that's what it is. So for number 4, the Rutherford-Gould experiment showed that electrons have negative charges. No. That protons have charges equal in magnitude but opposite in sign to those of electrons. That is a general true statement. Not always, though. If there's the number of protons and electrons are not always going to have equal charges if we just look at, the isotope example. But that's also not what Rutherford discovered either. So that's not true. The atoms have a tiny positively charged massive center. Yeah, that's our answer. But let's look at the other ones. The ratio of the mass of an electron to the charge of the electron. The ratio of the mass of an electron to the charge of the electron. That's not even valid, so ignore that. And the existence of canal rays, that was something Rutherford used to experiment, but that's not true and it's not important. So that would be C there, okay? Last question I have here is a Chapter 3 question. I know you guys are just starting Chapter 3 now or, heading into it, but I'm going to work through this example. You can end the video here and watch this later, but I do want to work through this example because it is a fairly simple one. So the question says to convert 15.8 grams of C2H6O2 to moles, molecules, and atoms. All right, so the first thing that I'm going to want to do is determine what we call the molar mass of this C2H6O2. Basically says how much does it weigh per 1 mole. So molar mass is defined as grams per mole. So how many grams of a substance do I have per mole? So in this case, what I do is I add up the number of atoms of each different species and multiply it by its weight. So I have 2 carbon. I'll indicate that with a little subscript of C. I have 2 carbon, and you don't have to memorize the weights of the atoms, but after doing it for so long, it kind of just will eventually remember some. So there's no need to memorize them off the bat, though. So the weight of carbon is 12 grams per mole. plus the weight of hydrogen. So I have 6 hydrogen, and hydrogen weighs 1 gram per mole, plus 2 oxygen, and oxygen weighs 16 grams per mole. So I add up 16 plus, I add 24 plus 6 plus 16 times 2, so 32. So 24 plus 16, like I said, I hate mental math. 24 plus 6 plus 32. So that should give us around 62 grams per mole. So that's the molar mass of C2H6O2. Okay. So now here comes the fun. So the first thing I'm going to do, so we'll call this kind of A, B, and C. The first thing I'm going to do is convert grams to moles. So that's the easiest you're ever going to have to deal with. So in letter A, we want to go from grams to, I don't like that, grams to moles. So here comes back stoichiometry. You know, I always said it's very important. So here it is, less than a week after you first learned it. So when I want to go from grams to moles, or really any of these conversions, molar mass is key. Remember, just like density is grams per mil and it's a conversion factor, so is molar mass. It's grams per mole. So if I'm given 15.8 grams of C2H6O2, I use the molar mass. That tells me for every 1 mole, I have 62 grams. Right, that's the definition of molar mass, moles per gram. You can flip it however you need it. Doesn't matter. If you need the grams to cancel, you put it on the bottom. If you need the moles to cancel, you put it on top. So grams cancel, and I'm left with moles of C2H6O2. So you can write mole as just, even if it's plural, you can just write MOL. That's fine, but you got to remember to put your units on these guys, or else they will mark it wrong. So 15.8 divided by 62. So that tells me that I have 0.254 moles of C2H6O2, but let's check the significant figures. Molar mass is a standard kind of measured value, so we don't look at the molar mass for the significant figures, just like how when you have a conversion factor of 1,000 milligrams per gram, you say that's an infinite, right? So we don't use the molar mass, we just look at this measured value, the 15.8. So I do want 3 sig figs, so that's good. Okay, next one wants me to go to molecules, so I'm going to go from grams to molecules. Now, we're going to have to use our friend, Avogadro's number, and that's equal to 6.02 times 10 to the 23rd atoms, molecules. You might see it written sometimes as formula units, etc. All the same thing. So I think of Avogadro's number as a counting unit. So think about a dozen, right? So if I have 12 dozen, 13 dozen, that tells me for every dozen, there's 12 whatever. It's a counting unit like that. So for every 1 mole, there's 6.02 times 10 to the 23rd of kind of whatever is in question. So in this case, I have 15.8 grams of C2H6O2. And I know that for every 1 mole of C2H6O2, there's 62 grams. So you got to start off the same way. Now I can go from, moles into, in this case, molecules. So for every 1 mole of C2H6O2, I have 6.02 times 10 to the 23rd molecules. Okay, So grams cancel, moles cancel, and I'm left with molecules. So this I need to get a calculator for. So we're going to do 15.8 times 6.02 times 10 to the 23rd. Make sure you put that in parentheses or else the calculator is going to get all annoyed and not do it right. And then divide that by 62. So I get 1.53 times 10 to the 23rd molecules. And in this case, we want to have 3 sig figs again. So that looks good to me. Okay. Molecules of what? You should really put C2H6O2. It's not a terrible big deal if you don't, but I just would to be safe. And then letter C wants us to go into atoms. So we want to go from grams to atoms. So really, you're going to copy the same, let's see if I can finagle this to work. Copy. Oh, would you look at that? Oh, that's not great. All right, it's fine for our purposes here. But basically, there's nothing different about what we did in the first step. This is annoying me. Hold on. There we go. I pressed the wrong button. Okay. The only difference between going from grams to atoms and grams to molecules is simply this unit at the end. Instead of it being 6.02 times 10 to the 23rd molecules, it now becomes atoms. So remember, from Avogadro's number, 6.02 times 10 to the 23rd can be of atoms, molecules, formula units, etc. So that's the only difference here, is it's no longer molecules, 6.02 times 10 to the 23rd, it's atoms. So it's 1.53 times 10 to the 23rd atoms of C2H6O2. Okay, now that's not always going to be the case where the atoms are like that and, kind of easy to deal with. Sometimes you need to go an extra step and once again say that one molecule of C2H6O2 has 6.02 times 10 to the 23rd atoms. But for this example, I would accept that as a correct answer. But moving forward through chapter 3, you'll learn that you'll need one more extra step in this conversion for it to be perfectly correct. But you're just getting used to it, so let's leave this video off. Thank you for staying through if you did, and any questions, be sure to let me know. All right, thanks. Bye-bye.